Exponential functions. So the first thing you guys want to look at when we're looking at exponential functions is like kind of what's its purpose, what's its use. A lot of times you hear on the news stuff about population. When they talk about the water level here on Earth and like global warming, and they're saying they'll use like it's doubling or tripling every year, right? And what this function allows you to do is it allows you to evaluate what is happening, what is the trend over a certain amount of time. So if your population started at 2 and it doubled every year, okay, 4, 8, 16, so on and so forth. But not everything is this simple, right? Sometimes you have bigger numbers, decimal numbers, maybe you're working with money, maybe you're working with a household, price of a house, and whatnot. So what you have is another parent function, okay? And some other parent functions we've seen in the past, it's just kind of like your x squared function or your rational function. You have all these parent functions we talked about, even just the mx plus b as a parent function. Some of these parent functions we've looked at. Now you have a parent function called the exponential function, where your variable or the amount that you're working with, like if you look at our parent function here, where we used to get a parabola and just kind of come out with a quadratic function of this, we would input numbers for what we would call here our base, okay? And the constant was the exponent. In this case, it's different where this is the kind of the piece that's being raised to a certain power, that's your constant. And this is your independent variable. Meaning, I could put whatever number in here, it does not depend on anything. This is the part that we could say, although yeah, these are variables, this is the part that varies the most, we'll say, where this is where I can manipulate, this is my input, this is where I can change that cupcake machine, saying, okay, instead of putting a certain 2 mix here, this is the part that changes. This is the part, content, I don't know, that's like a mixture of 2 words there. Constant, okay? Yeah, constant, this is the thing that stays the same. And then, yeah, we always look at this as our dependent variable. Because whatever I do here, and whatever effect it has on the constant, that's our dependent. And that's the whole idea that we've had about our input, output, as far as what a function does. So if you're looking at that cupcake machine, we like to talk about, okay, this is the part that, this exponent is the part that we're changing in, this b is the constant, the operator, and then, yeah, here our y's are. Now some things you want to look at is just kind of taking a look at what a graph of just using a nice number, y is equal to 2 to the x does. Okay, 2 being our base and x kind of being our input. Or now if you look at a table of this and you put in values for x, like -2, -1, 0, 1, 2, 3. If you put in inputs like this here, you'll see it has a trend. First, you see it has kind of some fraction results here. Now we remember that from kind of working with our rules of exponents. 2 to the -2 is really 1 over 2 squared, which is really 1 over 4. So we've seen that and the kind of effect it has, a negative exponent has. And then, any number raised to a 0 power is 1. Let me stick with the same color here, 1. And then you have 2, and then you see that doubling effect start to the doubling start to take effect. Now if you look at a graph, if you're looking at a graph, okay, what you have is a couple things. One, you have a graph that's increasing at an increasing rate. So it's going up, and as time is going on, we could say a lot of this will you know, a lot of what we deal with when we deal with exponential functions is usually this idea of time, and as time goes on, that's having a greater impact, and it's increasing at an increasing rate. So you have this kind of, now the other thing you have to consider is what we call here, and in this case, the x-axis becomes an asymptote. Okay? Funny word there, asymptote. Now what this asymptote does, basically, it sets a boundary. It's saying to you that this graph will never pass this kind of boundary here, because I cannot put any number here that will give me a result of 0 or less. You see that this graph will go on forever, and the number will just keep getting smaller and smaller. If you look here, it goes 1/4, -1/8, -1/16. It's getting smaller and smaller, but never, I'm sorry, this would be positive. Positive here, made a mistake there. Because our asymptote is 0, see, you understand something, you can see where you're making a mistake. This number will get smaller and smaller, but never to 0. And that's what this asymptote is doing. And you'll see in other cases where actually your asymptote, because if I add something here, my asymptote could go higher and I could have a different asymptote. But here you're just seeing this graph. It'll just, to nothing, but there'll always be some little gap there, and that's what you're dealing with your asymptote there. All right? And then this will keep, but you'll see it just kind of, but it'll still keep going this way, but it goes at an increasing rate there. Now some things you want to look at when we talk about this exponential function is your growth and decay. So this is showing some level of growth, right? And the reason for that is my constant is a number, or my base is a number greater than 1. So if I have this constant of a number greater than 1, okay, you'll see I'll have a growth, because I'm compounding basically a whole number here, okay? So let's say if I have y to the 1.4 to x, that's my function here. This would be some level of growth. When you start to talk about decay, okay, that's when you're taking your base, and having it a number less than 1. For instance, let's say I have, basically, I'm taking 80% of something, so for instance, I'm losing like 20% each year. This is an instance where you see decay, where actually something is going to, so I don't know if this is the exact graph for pointing to the x, but basically you see it's going to decrease at a decreasing rate. Here it's decreasing kind of fast, like your y value, your output is, but then it gets to a point where it levels off. And this is kind of more of a decay situation. And you can see that when you talk about, let's say, and we'll just use an arbitrary number like 500. Let's say you're taking a house that costs $500,000. We'll say it's 500, right? Bought a house for $500 in 1920, right? You could say, okay, it's increasing by 12% each year, and it did so for 20 years. Let's just even say 3 years, okay? And this, because this base, this is what your base, this is what the exponent is taking effect on, okay? This would be something that you would determine as growth. And I think this is after 3 years would be like $702. And you would see that on a graph. You'd start at 500, and then you'd see this kind of growth here. Well, let's say you took a car that you bought for $500, and it depreciates by 12% each year. And let's say you've had the car for 3 years. This is where the decay comes into place, because it's 80% each year. That car has become 88% of what it was the year before, right? And then you end up with a value of something like $340. This is your growth here, and this is your decay here. And this is kind of where this exponential, I really like this exponential function, because it starts to bring in growth of a house, growth of an investment, what your credit card is doing. You know, you buy a car, you drive it off the lot, and it just lost $2,000 worth of value in each car. Each year your car, you can buy a car in a certain year, never drive it, leave it in your garage, and each year the value goes down. And this is what this is taking into account of. And then where this will take us eventually is to what we call a logarithm, which will actually be able to determine, you know, how many years it'll take something to be a certain value. And then what we'll be doing with this exponential function actually is using that and determining like the bounce of a ball, saying on its first bounce it reaches a height of 10, and then second bounce maybe it's 6, and then each bounce gets, and that's the idea. You ever see a ball bounce, it kind of goes like that. And that's what we're going to be working with there. You guys have any questions?